Okay, previous chapter we already learned uh, what's the heat treatment corresponding to the metals phases, okay, and how to use the phase diagram and TTT diagram to specify our heat treatment for metal or alloys. Okay, and in this chapter we're gonna focus on the heat treatment of steels and cast iron. Okay, cast iron. And the objectives in this chapter, we have to know or we have to recognize and explain the various destinations of different classes of steels and differentiate it between the classes of steels and whether we can list the common alloying elements of steels and their purpose and explain various destinations for different cast irons. Okay, so let's look at this chart. It shows the category of metal and alloys, right? And in a big picture, that the metal and alloys can be classified into ferrous and non-ferrous. Okay, and the ferrous metals and alloys can be classified into steels and cast iron. Okay, and the steels can be classified into low alloy and high alloy. Okay, and the low alloy can be classified into low carbon, medium carbon content, and high carbon content. Okay, and cast irons can be classified into great iron, ductile iron, white iron, and malleable iron, and compacted graphite iron. Okay, and let's compare two different isothermal heat treatment. Okay, the first one is called the austempering. Okay, austempering is an isothermal treatment that involves in austenizing the steel and trenching to some temperature below the nose of TTT curve and holding at that temperature until all the austenite transfers into benite. Okay, and isothermal annealing. Isothermal annealing is used to form a perlite with more uniform properties across the steel cross-section. Okay, so let's look at this TTT diagram for this two heat treatment, two isothermal treatment, austempering and annealing. Okay, so if we want to get the benite structure, austempering should dominate this isothermal heat treatment. Okay, therefore we drop the temperature decrease substantially. Okay, below the nose, right? Below the nose, here, below the nose, right? And maintain this temperature to form the burnite, right? To form the burnite. Okay, for the isothermal annealing, that the temperature decreases above the nose, above the temperature of the nose, and the temperature remains constant until the perlite forms. Okay, and the transformation from austenite to perlite began at this moment, and the 100% of the perlite formed at this moment. Okay. Okay, so you have to know how, you have to realize how to use this TTT diagram to specify your heat treatment to get the specific structure, microstructure of this alloy that you want. Okay, the classification of metal alloys, as we already mentioned before, the metal alloy can be classified into ferrous and non-ferrous, right? If ferrous is steel, can be classified into steel and cast iron, right? For steel, the carbon content is or less than 1.5 weight percent. And for the cast iron, the carbon content should be within 3 to 4.5 weight percent. And for the cast iron, whose microstructure is ferrite, the microstructure of the cast irons consists of the ferrite and the cementite or graphite. Okay, or graphite. Okay. Okay, therefore the cast iron within the range of carbon content from 3 to 4.5, and for steel, its carbon content is less than 1.4 weight percent. Okay. Okay, therefore we saw the microstructure of cast irons are ferrite, cementite, ferrite, cementite. Of course, some graphite, carbon. Okay, carbon inside. Okay. Okay, for the steel, can be classified into low alloy and high alloy. That's mean the content of alloying elements. Okay. So for the low carbon, with this composition below 0.25 weight percent of carbon. Okay, for the medium carbon content is about 0.25 to 0.6 weight percent. And for high carbon content, it's about 0.6 to 1.4 weight percent of carbon. Okay. So for the plan is without any alloying element. For example, the steel 1010. Okay, 1010. Okay, and for HSLA, that's mean the high strength low alloy. The alloy elements include the chromium, vanadium, nickel, and molybdenum. Okay, like the steel 4310. Okay. Okay. Therefore, in this plan, it's only with the less than 0.25 carbon content in it. Okay. Instead for the medium carbon content, low alloy. Okay. For the plan, its carbon content between 0.25 to 0.6 weight percent. And for heat treatable low alloys with the alloy elements of chromium, nickel, and molybdenum. Okay, and for the high carbon content of low alloy, and with the planned low alloys with the carbon content between 0.6 to 1.4 weight percent. Okay. And for this tool steel, lower alloy with the alloy elements including chromium, vanadium, molybdenum, and tungsten. Okay, you can see the element content with tungsten, chromium. That's mean its hardness is extremely high. Should be high, right? Therefore, it can be used in the drills, saw, or dies. Okay. Okay, so for the tool, maybe it's belongs in between of the low alloy or high alloy. Okay, low alloy or high alloy. And for the high alloy, the stainless steel with the alloying elements includes the chromium, nickel, and molybdenum. Okay, and its applications are for high temperature, such as turbine or furnace, and with the very corrosive resistance. Okay, very corrosive resistance. Well, so it totally depends on your applications. Okay, For example, if I work on the pistons, gears, and for some weird applications, maybe heat treatable low alloy is suitable for your applications, but not the stainless steel. Okay, so it totally depends on your applications. And one thing we have to notice is that increasing strength and cost and decrease the ductility with carbon content. Okay, so you can see the strength increase and the cost increase and ductility decrease with carbon content, right? So it's a high carbon content, high carbon, and this side is low carbon. Okay. Okay. So let's look at the nomenclators for steels. Okay. For the iron-based irons, can be classified into steels and cast iron, right? Already mentioned it. And for the nomenclators for steels, 1, 0, 1, 1, 15, 40, 43, 44. 1, 0 means plain carbon steel. For the 1, 1 is plain carbon steel. And resulfurizing for machinability. For 1, 5 means the magnesium content as the alloying elements. And 4, 0 means the molybdenum content within the content of the 0.2 to 0.3 weight percent. In 43, with the nickel content, nickel, chromium, and the molybdenum content. And 44 with the alloying element of molybdenum content. And where the double X is the weight percent of carbon. Okay, weight percent of carbon. For example, 1060 steel is the plain carbon steel with 0.6 weight percent of carbon content. And stainless steel is usually has the higher content of the chromium, which is higher than 11 weight percent. Okay. So let's look at the this phase diagram is the total, I mean the whole phase diagram of the iron carbon steel. Previously, we just have this phase diagram with the carbon content at 6.67, right? We have an intermetallic compound, right here. So what's the name of this intermetallic compound? It's called this cementite, right? Cementite. Okay, only 6.6 carbon. Okay. And in this phase diagram, which is with the 100% of carbon content. Okay, and if we want a graphite foam in this alloy, we can add some silicon to promote the formation of graphite with slow cooling. Okay, with slow cooling. Okay. Therefore, here is some graphite content. This should be graphite and cementite. Okay. Okay, so for this cast iron, its range of carbon content is within here, this range. Right, I already mentioned here before, right? For this cast iron, right? 3 to 4.5 weight percent of carbon, right? Okay. Okay, roughly, okay, roughly within this range. Okay, so the strength or like hardness or the mechanical property is depending on the shape of graphite film in this cast iron. Okay, in this cast iron. In this cast iron and cooling rate. And the cooling rate. Okay, therefore for the lower carbon content, that means this carbon content is close to 3 weight%. Okay, with fast cooling, moderate cooling, and slow cooling that can control the morphology of graphite. Okay, for the fast cooling, we already know that the cementite form, right? Perlite and cementite. Okay, perlite and cementite. For the moderate cooling rate, the microstructure is perlite with graphite, and the graphite is in flake. Okay, that's graphite flakes. For the slow cooling, its microstructure is ferrite and the graphite with flake. Okay, graphite in flake, graphite flake. Therefore, we can realize that which one is the hardest one, or which one has the higher ductility. So what's the secrets of the hardness with this different cooling rates? Of course, we can know from its microstructure, right? For the fast cooling, perlite and cementite, right? Perlite for the moderate cooling rate, its microstructure is perlite and graphite flake. And for the slow cooling rate, its microstructure is ferrite and graphite flake. Once you see the graphite, once you see the ferrite, alpha ferrite, that means it has the higher ductility. Once you see the perlite or cementite, that means it's brittle. Okay, it's brittle. Therefore, the hardness with this 3 different cooling rate is the fast cooling rate. The hardness of the fast cooling rate is higher than the moderate, that of the moderate cooling rate, and the faster than the slow, higher than the slow cooling rate. Okay, and for the fast cooling rate, that its microstructure consists of a perlite and cementite called the white cast iron. And for the moderate cooling rate, its microstructure is perlite and graphite flake. Okay, and it is the palladic grade cast iron. Okay, and for the slow cooling rate, its microstructure consists of the alpha ferrite and graphite flake. Okay, and called ferritic grade cast iron. Okay, and for the higher carbon content, close to 4.5 weight% of carbon. Okay, with the moderate cooling rate, its microstructure is perlite with graphite, nodulous graphite. Okay, and for the slow cooling rate, its microstructure is ferrite and the graphite in nodulous. Okay, so which one's harder? Of course, moderate cooling rate of this cast iron has the higher hardness compared with that of the slow cooling. Okay, and the key structure here is perlite and alpha ferrite, right? The perlite's hardness is much higher than ferrite. Okay, therefore it can be called the palladic ductile cast iron with the moderate cooling rate with higher carbon content. Okay, and with the slow cooling rate, It's called the ferritic ductile cast iron. Okay. Okay. And when this microstructure form, we can reheat it at 700 Celsius for 30+ hours and cooling down with different cooling rate. Okay, with the fast cooling rate, the graphite morphology will change to rosettes. Okay, and for the slow cooling rate, that the pearl-like structure will transfer to alpha ferrite. Okay, alpha ferrite. Okay, therefore this layer structure, right? Remember that the pearl-like structure is the layer structure. Or we can say the lamellar structure can transfer to alpha ferrite. Okay. Okay. Okay, so I already talked about this previously. Say the great iron with the graphite flake, weak and brittle under tension and stronger under compression, and excellent vibrational damping and wear resistance. And good wear resistance. Okay, so if you want to make up some components which is withstand the compression, while great iron is a good choice. Okay, so let's look at the great iron. Okay, right here, great iron. Okay. For the ductile iron, that its graphite is in sulfurdite. It's sulfurdite. Okay, and the alloying elements are magnesium. Okay, magnesium, and graphite in nodules, not flakes. Okay, nodules, not flakes, and matrix often perlite. Okay, perlite. Okay. That means its matrix is layer structure with graphite nodules. Okay, graphite nodules. Okay. The white iron, remember, it is the hardest, one of the hardest cast iron, right? And it was the a silicon content, right? Silicon content, and it has more cementite. Okay, more cementite. Okay, so what's the classification of white iron? Right here, right? White iron, right? So I have the cementite layer structure. Sorry, perlite structure. Okay, perlite layer structure. Okay, with a cementite. Okay, with cementite. Okay. Okay, the label iron. Okay, and it can be heat treated at 800 to 900 Celsius. The graphite is in rosettes and more ductile. Okay, so it's the SEM. Okay, so this is the morphology of the of graphite. Okay, of graphite. Okay, and the compact graphite iron is with the high thermal conductivity, good resistance to thermal shock. However, with the low oxidation and elevated temperatures. Okay, elevated temperatures. Okay, so when you see this some compact graphite inside your matrix, such as this, okay, it's the graphite. It's the graphite. It's a graphite, and this is a graphite. Okay, so it depends on your applications. Okay, you can select the cast iron, the different type of cast iron that you want. Okay, so for this compact graphite iron, well, maybe it's not good to operate it at elevated temperature because its oxidation ability is poor. Okay, however, it has a good resistance to thermal shock. Okay, thermal shock and with the relative high thermal conductivity. Okay, so we can compare with those cast iron. First is the gray iron with graphite flake, right? Graphite flake is a great iron. Oops, it's a great iron. Okay, it's a great iron. Cast iron. Okay, so how about the second one, the figure B? So which type of this? Figure B. Well, here it says cementite and perlite. Right, cementite and perlite. So it must white. Right, white iron or white cast iron. Okay, for the figure B, its graphite morphology is nodulous. Okay, it's nodulous. So it's a malleable iron, cast iron. And the figure D, the graphite shape is spheroid, okay, or nodulous. It's more like a sphere. It's more sphere. Okay, more sphere. Okay, therefore it has the higher ductility, has a higher ductility. Okay, and in figure E, it shows the compact graphite cast iron. Okay, compact. Well, you can see for the graphite flake, right? For the compact graphite, that's mean the graphite stack, right? Stack, compact, okay, compact stacking of the graphite layers, okay, graphite layers. Okay. So the limitations of ferrous alloys are relatively high density. That means the weight is high, right? Its weights are high, and relatively low electrical conductivity. Okay, and the poor corrosion resistance. Okay. Okay, let's look at the non-ferrous alloy. Okay, like for example, the copper alloy, like brass. Brass is with the alloy element zinc. Okay, zinc is the substance and the impurity. Okay, using the custom jewelry, coins, corrosion for corrosion resistance. Okay, like a bronzo. Okay, its alloy elements are tin, aluminum, silicon, nickel. Okay, can be used as a landing gears. Okay, landing gears. And so on, like the titanium alloy, lower density, okay, compared to steel. And it's reactive at high temperature, especially be used in the space industry. Okay, and for the noble metal, noble metal such as gold, silver, and platinum, and so on. It has a very good oxidation resistance and very good corrosion resistance. Okay, well, so for these noble metals are not being used in some structure, of course. Okay, or you will be bankrupted, right? Okay, you cannot use gold as a pillar, as a column, right? Or as the component, as the machine components, right? So those kind of noble metals usually are using kind of a surface coating for electro coating or for some jewelry, okay? It's or for some catalyst, okay, for some catalyst. In aluminum alloy, its density is about 2.7. It's lower than that of the titanium alloy. And with the alloying elements of copper, magnesium, silicon, magnesium, magnesium, and zinc, and so on. Okay, and start hardening solid solutions or precipitation. Okay, okay, can be used in structure, aircraft parts, packaging. Okay, and for the magnesium alloy, well, its density is very low. It's about 1.7. It's much lower than aluminum alloy, right? And it ignites easily, okay, and can be used in the aircraft, missiles, right? And refractory metals, especially have to be using in high temperature environments, okay? Therefore, those refractory metals has a very high melting temperature, okay? It's high melting temperature, okay? Niobium, molybdenum, tungsten, okay, tantalum, okay? And the third type of annealing for the ferrous alloy. Annealing is heat this kind of metals to the anneal temperature and cool down slowly. Okay, what's its its performance or its application of the annealing process? First is stress release, right? Why we have to release the stress, or say pre-stress or residual stress. Okay, those stress could be caused by the plastic deformation or non-uniform cooling or phase transformation. Okay, or if we want to make a very soft steel, right? The sulfur dies steel is the approach, is the process to make very soft steel, and to make it is a good machinability. Okay, and you just need to heat up below its equilibrium temperature or your tactile temperature and hold it for 15 to 25 hours. Okay, okay, and the process of annealing is the negates effect of cold working by recovering and recrystallization. If we need this recrystallization, that means the grain site regrows. Okay, regrows. We have to adjust its mechanical property. Okay, and we can use annealing process. We can use annealing process and so on. And the different type of annealing, such as the full annealing of steel, right? We'll make a softer steel for good from foaming by heating to get austenite and cool in furnace to get coarse perlite. It's called a full annealing. Okay, I'll introduce this later. And the other process is called the normalizing. Normalizing as to deform the steel with large grains, then normalize to make grains small. Therefore, the full annealing to get coarse perlite, and normalizing is to get fine perlite. Okay, fine perlite. Okay. I already mentioned this. I already mentioned this before, right? Annealing and normalizing. Annealing here is the full annealing. Okay, full annealing. If a full annealing and normalizing can enhance the dispersion strengthening. Okay, different steels can be dispersion strength by controlling pearlite fineness, right? We already mentioned this in previous chapter. Okay, steel is initially heated to create homogeneous austenite. Okay, homogeneous austenite, that's the alpha phase, right? And annealing is the slow cooling of steel to produce coarse pearlite. Okay, well, cooling from the austenite with the slow cooling rate to get coarse pearlite. Okay, and this homogeneous austenite cooling with fast cooling rate in air, we can get a fine pearlite. And this process is called the normalizing. Okay, so annealing, we get the coarse pearlite. Normalizing to get fine pearlite. Okay, and sulfur dicing is the other annealing process that can improve the machinability. Okay, it deals with high cementite has poor machinability, right? We already mentioned that this with the high cementite content, that means its hardness is also high. It's also high. So how to modify its hardness or how to modify its mechanical strength and sulfur dicing is one of the process. Okay, and the sulfur dicing is heating over several hours at 30 Celsius below the equilibrium temperature, or say the eutectoid temperature. Okay, and this changes the cementite phase morphologies into large spherical particles. Okay, cementite phase transfer to spherical particle. Okay, it's called the sulfur dicing. Okay, sulfur dicing. The resulting sulfurdite microstructure has a matrix of soft. The matrix is soft, which is a machinable ferrite, right? Alpha ferrite. Okay, after machining, and the steel can be given a sophisticated heat treatment to achieve the desired property. Therefore, we can sulfurdize this alloy to make it machinable. And after machining, we can process a different heat treatment to achieve the desired property. Okay. Okay, so we can see this kind of annealing process of this in this figure. If we want to do the sulfur dicing process, we just to reach the temperature below the TE, right? The TE right here is the in1, the TE, right? For a couple of hours. Okay, it's for the iron and carbon system. Okay, and for this normalizing, after cooling this, the temperature should cool to the range here. This blue range here. It's normalizing with different carbon content. Okay, with different carbon content. Okay, and for the full annealing, temperature is within this great region. Okay, within the great region. Okay, the great region is here. Is the full annealing process. It's just above this region. It's for the full annealing. Just above the equilibrium temperature, right? Okay, just above this equilibrium temperature. Okay. Okay. So this just look at the mechanical properties corresponding to the different annealing process. Okay. Okay, so for this, let's look at, for example, for the normalizing process. For the normalizing process, this is a normalizing with different carbon content, right? It's the normalizing process. This is a normalizing, right? This is annealing. Okay, and this is the normalizing, and this is annealing. Okay, and this is the annealing. Okay, and this is the normalizing. Okay, so what's this figure tells us? What this figure tells us? Okay, so this figure tells us for this tensile stress, for example, for the UTS, right? For the tensile, if we're gonna modify the tensile stress of the plain carbon steel, how to modify it? Well, we can use the normalizing and annealing process to control its tensile stress. Okay, within, for example, if we have the carbon content about 0.6, right? 0.6 weight% of carbon. Okay, therefore we can control its tensile stress UTS within this range by normalizing or annealing process. Right, and with the higher carbon content, say 0.8 weight%, right? Therefore, we can control its tensile UTS in this region, right? We have a higher range of UTS with 0.8 carbon content by normalizing or annealing process. Okay, the same if you want to modify its unit stress with 0.6 weight% of carbon, the range of the yielding stress is in this range, right? And with the 0.8 weight% of carbon content, by normalizing, annealing, its unit stress is within this range, right? Okay. Okay, so you can follow the same ideas to analyze this figure, okay, to figure out what's the optimum mechanical properties that you want or that you designed. Okay, for example, you already have the alloy with martensite structure. Okay, and how to modify to reach that tensile stress or the unit stress that you want. Okay. Okay, so let's look at the heat treatment with TTT diagram, right? For this yellow curve, it shows the annealing process, right? It shows annealing process, and the austenite begins transfer to perlite at this moment, right? And it finish, that's mean the 100% of perlite structure foam at this moment, right? So the process went from here to here, right? And for the trenching process, that's mean the cooling rate is extremely fast, okay? Therefore, this cooling curve, right, decrease substantially, very fast, And this cooling rate, this cooling curve didn't intercept or didn't have the intercept with this TTT diagram, right? You can see the nose is right here, right? Nose is right here. And this cooling curve didn't touch this kind of nose curve, okay? It didn't cross this nose curve, okay? Therefore, for this trenching process, it is impossible to have a transformation of perlite, okay? Because this cooling curve even didn't touch this nose curve, okay? And the final one shows the tempered martensite. That means we have to modify the mechanical property of the martensite structure, right? And we can reheat it at a specific temperature, right? We can reheat it at a specific temperature and hold it for a specific time, and then cooling, right? And we can modify its mechanical property, such as the hardness, okay, hardness. Okay, therefore you can see in this region is martensite and austenite. Okay, martensite and austenite. Okay. Therefore, the atoms doesn't have time for diffusion. Therefore, for the trenching process is diffusionless. Okay, it's diffusionless. Therefore, you can see in this region, there's no perlite, right? No perlite structure because this trenching process is diffusionless, and this cooling curve never touch the nose curve. Okay, the nose curve is right here, right? It's the nose, right? And this is the cooling curve. Even the cooling curve never touched the nose curve. Therefore, the austenite is impossible to transfer to perlite. Okay. Okay, so let's look at the other mechanical properties. It's called the hardenability. The hardenability is the ability to form the martensite, and the Germany and trench test is the measurement for hardenability. Okay, so how is this Germany and trench test? I mean, we have the steel rod, okay, and one end is fixed, right? And we have some water, 24 Celsius water sprayed on it, okay, sprayed on it. And this specimen, this steel, is heated to austenite phase, okay. Okay, and then we get a flat ground, and we measure the Rockwell hardness at each point from the surface, okay, to the center of the specimen. Okay, therefore we can see this curve of hardness versus distance from the trench end. And this end is the trench end, right? At this position, right? Therefore, at the surface has the highest hardness. That's for sure, right? Because you get kind of a trench process at the surface. And the hardness gradually decrease with distance of displacement, right? You can see this hardness gradually decrease, okay, from the trench end to the center of the displacement. Okay. Okay. So that's the hardenability test specimen, this equipment for this test. Okay, I already mentioned that the specimen is a cylindrical bar with the 1-inch diameter. Okay, and with the 160 inches flat surface. At one end is austenited and is trenched. Okay, and the Rockwell hardness is measured up to 2.5 inches from the trench end. Okay, trench end. Okay, so let's look at the hardness test with the TTT diagram. Okay, the hardness with correlated to the TTT diagram. Okay, so this is our specimen, right? And we have the flat surface right here because we have to measure the hardness. Okay, therefore at the trench end, the surface has the highest hardness, and the hardness gradually decrease with distance from the trench end. Okay, from the trench end, right? Okay, therefore we can find at the surface. This is the cooling curve. Okay, this is the cooling curve for this test. At the surface is the cooling curve. At the surface of this Germany trench test. Okay, therefore you can see this curve didn't touch the nose curve of TTT diagram, right? So the nose curve is right here, right? Just this, right? Therefore, the austenite will not transfer to perlite at the trench end. Okay, the trench end. Okay, we have found the martensite structure. We have found the martensite structure. Okay, and this austenite surface, right? The austenite will transfer to martensite. Okay. Okay. Okay, and at the second point, the point close to the trench end, but not the trench end. Okay, so therefore the cooling curve is touch, right? Oops, it touch the TTT curve, right? It's touch here. Therefore, some of the austenite transfer to perlite. Okay, some of the austenite transfer to perlite. Therefore, the structure of the second point shown in this figure consists of the martensite and perlite. Martensite and perlite. Okay. And for the next point, right? This the third cooling curve. Right? The third cooling curve is right here. And the austenite start to transfer to perlite at this moment and finish at this moment. Okay, so what's this cooling rate, a cooling curve tell us? What's this cooling curve tell us? That means at this point, its microstructure is fine perlite, right? Because as I say, at this point, the austenite completely transforms to perlite. Okay, and at this point, so this is its cooling curve. Of course, it's the same. It's still the perlite structure, right? And it start the austenite start to transfer to perlite at this moment, and the 100% transformation of perlite at this moment. Okay. And the hardenability versus alloy composition. So we see there's a different cooling rate. For example, our carbon content is 0.48%. Okay, and with different alloy, 1040 and 4340. Okay, and with the different cooling rate. So what's this figure tell us? Okay, for the 1040 steel, its trench end has the highest hardness, right? Has the hardness, and the hardness reaches 20 for HRC. It's at the distance from the trench end about 18 millimeter. Okay, 18 millimeter. And for the alloy about the 4340, of course, the same as highest hardness is located at the surface, right? And with the distance, its hardness, well, it's not decreased dramatically, right? Okay, it's not decreased dramatically. And at the distance about the 40 millimeter from the trench end, its molten site is about 80%. Okay, therefore, its hardness still high, right? At of 5 centimeter from the trench end. Okay, therefore you can compare with the different alloy, different steel. Okay, different steel, like 4140, right? At the end of 40 millimeter from the trench end, well, its modern size about like 40% of modern size. And for the 8640, and its modern size composition is about maybe 30, okay, at 50 millimeter from the trench end. Okay, and for the alloy steel, I already mentioned that in the previous chapters that the curve, the TTT diagram, the curve was shifted from A to B. You can see this figure. Okay, so this is alloy. For the curve B is alloying with alloying. Okay, A is the iron carbon system, and this steel or cast iron, the ferrous metals with alloying, this curve will shift from A to B. Okay, so what this figure tells us? What this figure tells us? The nose shifted, right? The nose of A curve was right here, shift to here. But what's that mean? That means the molten side is easier to form, right? Because the curve shift, the nose shift, right? For the A curve, that the heat, the cooling curve should be like this, right? To form the molten side, right? Because this cooling curve cannot touch the nose or cannot touch it, right? That means the austenite will never begin to form the perlite. Okay, so if my cooling curve like this, what's that mean? That means part of this austenite begins to transfer to perlite, right? It will start to transformation at this moment, right? And if these alloy steels, that means the nose shift from A to B, right? Therefore, the heating curve of this, the cooling curve is this blue one, the molten side still form, right? However, for this blue blue cooling curve, it has the intercept with the curve A, right? For the A curve. So the austenite will begins to transfer to perlite at this moment, right? And 100% of the perlite will film at this moment, right? And for cooling B, well, this blue curve never touch the nose, right? Never touch it. Therefore, the molten side is easier to film. Okay, and the decomposition of austenite to ferrite is the light. Okay, so these two process, I mean, these two kind of transformation. Okay, it depends on the alloying steel, the alloying elements. Okay, because the shift of TTT diagram, the shift of the nose curve. Okay. Okay, so today's course will be ended here, and we'll see you next time.